Right, so last part of section 5.1 picks up right where we left off. Last thing we did yesterday was we changed polar to rectangular. Right? And Andrew, can you remind me the two trig functions that we used to do that?
Radius cosine theta equals x, and radius sine theta equals y.
Yeah, so we use sine and cosine. So the only trig function we didn't use was tangent. And that's, or inverse tangent, is what's going to come up here. All right, so when you have a point in rectangular, Courtney, what are the two letters that we use when we're talking about rectangular?
X and Y.
We use an X and a Y. So what's going to happen today is you're going to be given an X and a Y. And they're going to want you to change those into the other two letters. Justin, what are the two letters we use when we're doing polar?
Radius and theta.
Radius and theta. So we're going to have to find the R and the theta. Okay. So let's pretend that this is a point in X comma Y. Okay. Brianna, which letter there is the horizontal? X. And Y is the vertical. So what I'm going to do is just put in, it's a little longer than I need, but that's okay. I'm just going to put in a vertical line right there. So now I can see this. I can see how far to the right I went. That's the horizontal. That's the X. And I can see how far up I went. That's the Y. Okay. Any questions on that? Now, yesterday, those are the two things you had to find. Today, those are the two things that are going to be given. We have to find the R and the theta. Cal, what does R stand for again?
The radius.
It's the radius. So the radius is the distance from the center of a circle to the edge. So pretend like this point right here. Let's pretend that that point is on some kind of circle. How big of a circle? I don't know. That big. All right. And I'm going to draw in the radius. That's the radius. I don't know how long that is. Could be 1 unit, it could be 12 units. There could be other circles on here. Doesn't matter how long it is. Let's just call that R. Now, that's R, but if you look at it in terms of that triangle, it's really the what of that triangle? It's the hypotenuse. So there's a theorem we can use from geometry, as long as you know 2 out of 3 sides, you can find the third one. What theorem can you use to find a side that you're missing in a triangle? Yeah. So in a minute, I'm going to write this down nicely on the next page. X squared plus y squared equals r squared. That's how you're going to find the radius. Okay, and again, I'm going to write this very nice and organized on the next page. Okay, so that's your radius. Matt, what's the other thing I need besides my radius?
Your theta, your angle.
Yeah, I need my angle. That's my angle, right there. Right. So to figure out that angle, we're going to use this side, which is given, and this side. We're not going to use R, because R is going to be something we find, and we've talked about why we don't want to use things we find. So let's name these two sides. Emily, what's the name of the side that's X from the perspective of theta?
Is that adjacent?
That's adjacent. Yep. And Abigail, how about the side that is across from theta, that we've labeled Y?
Opposite?
That's opposite. And I've already kind of mentioned this yesterday. The only trig function we haven't used yet is tangent, and tangent is opposite over adjacent. So in this case, tangent equals y over x. Now, we don't really want the tangent of theta. That's not what this coordinate says. This formula says theta. So how would I get rid of tangent? We're going to do inverse tangent. Okay, and I'm going to write that down nicely on the next page. But that's the basic idea of what we're doing. Okay? Using Pythagorean theorem to find r, and then we're going to use tangent to find that angle. So, first thing we want to do when you're converting from rectangular to polar is graph the point, this is what you practice in the homework, and just figure out what quadrant it's in. You'll see why the quadrant matters in a little bit. Now, you have to determine r and you have to determine theta. You can do either one first. It's up to you. I don't know, whatever one I feel like doing first. So in the directions I'm giving you, I'm doing theta first. So if you're in quadrants 1 and 4, the formula is exactly what I just showed you on the other page. We had tangent of theta equals y over x. We want to get rid of tangent. Isaiah said use inverse tangent.
Yep.
Perfect. Theta equals inverse tangent y over x. And that works fine if your coordinate is anywhere on this blue area. That's quadrants 1 and 4. The problem is you might not always have a point in quadrants 1 and 4. You could get an answer in quadrants 2 and 3. Well, this formula by itself will never give you an answer in quadrant 2 or 3. The definition of inverse tangent is to always give you an answer between negative 90 and positive 90. Always. It will never give you anything else. But you could definitely have a coordinate over here. So how would you figure it out if that formula would never give you an answer over there? Well, we just have to make a small adjustment to it. We're still going to do inverse tangent of y over x. But if you want to go to the other half of this circle, okay, the left half, you have to add 180. You have to add 180. Or if you're doing it in radians, it would be pi. That's why I had you do step 1. If you don't have to graph the point here, you can figure out the quadrant in your head without graphing it. That's fine too. Just make sure you know what quadrant you're in. So quadrants 1 and 4, use the top formula. Quadrants 2 and 3, use this one. Now, this doesn't cover everything. Where else could you be besides quadrants 1, 2, 3, or 4? Yep. Well, it's usually going to be on a circle somewhere. So you could be at the origin, but most of the time I'm going to give you a point somewhere on that circle. Yep.
The axis?
You could be on an axis. So, okay, well, what's the problem if you're on an axis? Let's look at that point. What's the x coordinate of that point? 0. And the y coordinate? Well, the y, remember, y is not an angle. Y is just a number you went up. The up, we don't know what the up is. It's something. Maybe it's 2, 3, 4, whatever. But the important thing is the x is 0. Well, what would happen if you try to plug in a 0 for x in either one of those formulas? Yeah?
There's gonna be no solution.
Why? Why? What's wrong with plugging in a 0?
It's like you can't divide a number by 0.
You can't divide by 0, right? So it's not there isn't going to be a solution. It's that these formulas wouldn't work. If you're on an axis, right, that's the simplest kind of angle to figure out. You only have 4 options: 0, 90, 180, 270. You don't have to use a formula to figure that out. Okay, so if you are on an axis, just remember that your angle has to be 0 if you went right, 90 if you go up, 180 if you're left, 270 if you're down. So other than being on an axis, use one of these 2 formulas to figure out your angle. And that finding the angle is totally separate from the radius. You don't need one to do the other. So now, what formula did I say, or somebody said it to me earlier? We're going to use the Pythagorean theorem. Doesn't matter what quadrant you're in. That's always the formula to find your radius. Right, so we'll try maybe 1 or 2 examples of that, and then that'll be it for 5.1. Good. Okay, so there's a coordinate, 2, -2. And they want you to convert that to polar.
What was the formula for radius?
What's the what one? Yeah. Okay, so 2, -2. Megan, can you tell me first what quadrant is 2, -2 in?
4.
It's in quadrant 4. Now that we know that, we should be able to figure out the formula for theta. Gabe, can you tell me what is the formula to find theta if I'm in the 4th quadrant?
Theta would be the inverse tangent over x.
Yep, inverse tangent of y over x. What's y in this case? -2 and x 2. Okay, so inverse tangent of -2 over 2. And what's -2 divided by 2?
-1.
Just -1. So when I type that into my calculator, I'm just going to type in -1. All right, so let's go. After you turn your calculator on. I'm in degrees. You could be in degrees or you could be in radians. My suggestion would be always do it in degrees first. Convert it to radians by hand if that's what they want. And there's a reason I'm saying by hand. Right, so the angle is -45. Now, there's nothing wrong with that angle, that's fine. -45. But remember what we did yesterday. There are usually four different ways to write a point in polar. So maybe on the test, if this is multiple choice, I'm going to write -45 as a positive. So what can you add to -45 to make it a positive number? You can add 360 to it. If you added 360 to that, what would you get? 315. Both of those are correct. Which one would I want? I'll make sure I write that in the directions. I'll either say make sure your angle is positive, or if you get a negative, you can leave it. I'll let you know. All right, so we got our angle. Alex, to find my radius, what theorem am I using?
Right now it's -10. And that was the one before.
To find my radius. So we're done with.
So R2 equals x equals y2.
All right. So r squared equals what's x squared in this case?
2.
X is 2. What's x squared?
4.
4. X squared plus what's y squared?
4.
4 again. Okay. So we get r squared equals 8. And now I just have to get r by itself. So Riley, how do I get rid of that exponent of 2?
You have to square root them both of them.
Yep. Take the square root of both sides. Now remember, square root of 8, that is a root you can simplify. We practiced that way back at the beginning. Anybody tell me how the square root of 8 simplifies? Yep.
2 square root of 2.
Yep. If you're not sure how we get that, one way is to go like this. Factor the number 8 into 4 times 2. And now take the square root of 4. All right, so we've got our radius and we've got our angle. Let's just practice writing this answer a few different ways. So one answer is 2 square roots of 2, comma, -45. Perfect. That answer is just fine. You could also do 2 square roots of 2, 315. I'm not going to ask you more than one way on the test. but I'm just showing you some different ways. Let's see, where are we? Right to, down to. So we basically did this one. That's the first one we did. Right, negative. We also did right, positive. That's the second one. I'll do one with a negative radius. Let's do negative 2 square root of 2. That means I'd start by going to the left. Let's go like that. And how much would it be to get right there? What would that angle in blue be? $135. This is 45 right here. We know that because it's right in the middle. If you go that far, it's 90. And then you go to the middle of the next one, that's 45 more. So that's 135. I'm not going to keep writing different ways, but these are all different ways you could do it. I did 3 out of the 4. Now, if they wanted this in radians, my suggestion was do it in degrees first. Because let's change one of these to radians by hand. Just the top one. Okay. The radius would stay the same. 2 square roots of 2. Now, negative 45. We always multiply by a fraction. Does anyone remember if I want to change degrees to radians, is it 180 over pi or pi over 180? It's pi over 180. Degrees is in the top. If you're trying to cancel it out, you want degrees in the bottom. 180 always goes with degrees. Pi goes with radians. Now, watch what happens. 45 goes into itself once. Goes into that 4 times. You're left with negative pi divided by 4. And that's how you'd write that first answer as a radian. Now, watch what happens if you type in the original problem and put your calculator in radians instead. So I'm going to go put it in radians. And I'm going to go type in the same thing. Did I get negative pi over 4? What do you think? I mean, should that be negative pi over 4? If I did everything correct right here? It should be. Did anybody recognize that number as negative pi over 4? No, you're not going to. Unless you magically have all these decimals memorized, which even I don't. So if you use the calculator to do a problem in radians, it's going to give you a decimal. It's not going to give you a fraction with pi. 90% of the time, we always write radians with pi. We never write negative 0.785398. We don't write that. Right? And there's no way the calculator can convert that to negative pi over 4 for you. So that's why I said do it yourself off to the side, and you will get the negative pi over 4. The calculator can't give that to you. All right, we'll try one more of these. I'm not going to write it 4 different ways, though. Okay, let's just let's try this one. Okay, negative 4, negative 5. Stephen, what quadrant is this one in?
That would be on the third.
Yeah, roughly right there. Good enough. It's left and down. So Jason, if I'm in the 3rd quadrant, what's my formula for theta?
180 plus inverse tangent y over x.
Yep, 180 plus inverse tangent y over x. Is it okay to cancel the negatives? Anything? You sure? Yeah, it's fine. It's just -5 divided by -4. So if I cancel them, it's just less I have to type in. Okay. That's not going to be a nice answer. So what we're going to do in this one is we're just going to round. We're going to round things off. The last one came out nice because it was a multiple of 45. This isn't. So second inverse tangent of 5/4. Since I'm going to round it, I can choose at this point, radians or degrees. The directions on the test will tell you which one I want.
Why you do 180?
Why do you have to add the 180?
Yeah.
Because we're in quadrant 3. Whenever you're in quadrants 2 and 3, you always have to.
180 or pi?
Same thing. It depends. If you're in radians, pi. If you're in degrees, you want to add 180. So I'm just doing the first part to show you something. 51 degrees. That's not in quadrant 3. Quadrant 3 is between 180 and 270. Right? That's why we add 180 to that, and it's going to get my answer in quadrant 3. Okay, 231.34. Perfect. It's right in there. Not a multiple of 30, not a multiple of 45, it's just a random decimal. So we'll round it. Okay, and since I rounded the angle, I might as well round the radius as well. Okay, we'll round both. So r squared equals, Pat, what's x squared?
16.
And y squared? Yep. So r squared equals, Elizabeth, what's 16 plus 25? 41. And Andrew, my last step is to do what of, take the what of 41?
Square root.
Take the square root. Yep. So r is the square root of 41. Okay, let's see what we got. 41 square root, about 6.40. Okay, so now just write your final answer. R is the distance from here to here, which is really like the hypotenuse of a triangle. And your angle is that right there. It's 231.34. And that is how you convert from rectangular to polar. Okay. Any questions on that? Okay, so let's look at the last thing. So, the last part is in Appendix 4. That's in the back of the book. It's in the appendix because that's really stuff that comes from like Algebra 2, more of a review. But it kind of helps just to go through it, and it's a little bit easier kind of material. So we'll go through it. The connection between what we just learned in section 5.1 and what I'm teaching you in this section, you would actually see the connection in 5.3 part 2. We're not doing 5.2 part 2 because we have Monday off. So it's kind of like we're going to learn two things, but we're never really going to get to the point where we would connect them and see how they're connected. Just the way the schedule worked out. All right. So what I'm going to try to show you is where complex numbers fit into the diagram of like other kinds of numbers we know. So I'm going to start with the simplest kind of numbers and then work my way out to more and more complicated ones. Kind of trying to explain to you each time why we need more complicated numbers. Why don't we just keep things simple? Why? Why do they get more complicated? So the simplest kind of thing you can do with numbers is count. Okay? So like the first thing you learn how to do. So those numbers in that middle box, the innermost one, are called counting numbers. Okay, counting numbers don't don't include negatives, no such thing. Nope, no decimals, no fractions, not even the number 0. Because when you count, you don't start 0, 1, 2. Right? You count 1, 2, 3. You start with the number 1. Now, the reason for getting into more complicated numbers, I'm going to try to explain it with arithmetic. If you want to do addition with counting numbers, you would never run into a problem. Someone in this room could pick any counting number they want in their head. Someone else could pick another counting number. And I could add the two together. And the answer would be another counting number. It wouldn't be an issue. But let's look at something like subtraction. Riley, can you give me a counting number?
4.
4. I'm going to subtract the same counting number. That's a counting number. That's a counting number. I'm subtracting 2 counting numbers. Is the answer that I get a counting number? No. So, if somebody doesn't believe in the number we know, 0, there's no such thing as 0, they don't believe in it, then you'd have to say it's impossible to do this problem. There's no such answer that you could ever write. So what did we do? We invent a number, and this number basically is the number that represents having nothing. The number 0. And those are your whole numbers. So the only difference between whole numbers and counting numbers is now you've invented the number 0, so you could handle a problem like that. And I think it makes a lot of sense to have the number 0. If you have $4 and you spend $4, how much money do you have left? It'd be kind of nice if you could write a number that represented your amount of money left. And we make it like a circle. So at this point, I think the reason for the number 0 is kind of common sense. It's still in the realm of things people would do with everyday math. We haven't got to things yet that are really outside that. But we will.
Is 0 the only whole number, or is it like other?
Whole numbers include everything you had before plus. So whole numbers are the addition of the number 0 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and keep going. So now we've solved this problem. But let's take 2 whole numbers that are different. Okay, Emily, can you just give me 2 whole numbers?
Can they be like 0 and 5?
Sure. She said 0 and 5. Now, I have a whole number minus another whole number. Is the answer here a whole number?
Yes.
It's -5.
That's still a whole number.
No, it's not. Whole numbers are positives.
Whole numbers only are 0 and up. No such thing as negatives. Forget about negatives. They don't even exist in whole numbers. So, you can't do 0 minus 5. If you're saying, yeah, you can, it's -5. No, it's not. If you don't believe in negatives, then it's not -5. There's no such thing as -5. It doesn't exist. This is starting to get a little bit more abstract. How could you have $0 and spend 5? Well,
You'd be in debt.
credit card, right? You could have no money and just charge something. So now, yeah, you're in debt. So maybe to somebody that's like 2 or 3 years old, they wouldn't really understand that. Like if I said, I'm holding 2 objects, how could you take away 3 from me? Well, you can't. I only have 2. How can you take away more than I have? That's impossible. But it's not impossible. You can take away more than you have.
Bless you.
Bless you. And that's like being in debt or a negative. Okay? So I think for most everyday purposes, negatives still make sense. Businesses sometimes lose more money than they make. That's a negative number. Right? Definitely uses for negative numbers. And now, once we introduce negatives, we have the idea of integers. So integers include everything you had before plus negative numbers. So now we're looking at like -3, -2, -1, 0, 1, 2, 3. Now, addition, subtraction, multiplication, no problem with integers at all. Someone in this class could pick any integer they want. Somebody could pick any other integer. I could add them, I could subtract them, I could multiply them. And the answer would always be an integer. What operation could mess me up a little bit with integers? where I do this and the answer isn't an integer? Division. Right? Division. Someone give me an example of an integer divided by an integer, and the answer is not an integer. Yeah?
2 divided by 3.
Sure, 2 divided by 3. What are we going to do now? Right? You know, it's like saying, here's two objects. Or if I had 2 $1 bills on me, and I want to divide that out to 3 people. All I have is 2 $1 bills. I can't do that. Okay? The only way I can take something and divide it if it doesn't go in evenly is to start breaking things into pieces or parts. Right? You want me to divide these 2 things equally between 3 people? Well, then I have to break a little bit off of one, break a little bit off the other, and give those 2 pieces to someone else. Right? So they're only getting a fraction of something, or a part of it. Right? So that's the next kind of numbers that we've invented. Right? Going beyond just having nice whole numbers or integers, now we can have fractions or parts of a number. Right? And those are your rational numbers. For most everyday purposes, that's about as complicated as most people need. Right? When you're cooking, you might use 2/3 of a cup. It's not quite 1, it's a little less than 1. It's a fraction of a cup. When you buy something at the store, it might cost $12.99. It's not $12, it's not $13, it's 12 and then a fraction of the next dollar. Right? But it's still a fraction. So we have rationals, and then we'll look at the, All right, so we have rationals, which are all the numbers you can write as fractions. And then we have numbers you can't write as fractions. Okay? Those are irrational. Now, when you start to deal with irrational numbers, you're starting to get into numbers most people don't use in their everyday life all the time. Anybody think of a number that you cannot write as a fraction? See, this is harder. That's my point. Yeah.
I was gonna say pi.
Pi.
Okay.
Pi is irrational. Pi is still a number some people might use. Like if you do any kind of stuff with circles or cylinders or machining parts, you might use a computer that has pi built into it for maybe making the circumference of something. Other numbers that use pi, that you can't write as fractions are square roots. Not like the square root of 4 or the square root of 9. Those come out nice. I mean square roots that don't come out nice. And it's not like you could say, well, maybe someday will we figure out how to write the square root of 2 as a fraction? No, never. I could prove to you it can never be done. It's impossible. No matter how good computers or whatever gets, it is never going to be possible to write the square root of 2 as a fraction. Never. Where would square roots come up? Sometimes if you're measuring like a diagonal, right? Using a Pythagorean theorem to measure a diagonal. So who would use Pythagorean theorem? Maybe a carpenter. Although they probably wouldn't need to use square root of 2 because think about how many decimals that has. It goes on forever. Most carpenters, if they're going to measure something, like if you're building, depending on what you're building, you're not going to need that kind of accuracy. They're just going to round it. Okay? Maybe they need to round to the nearest inch. Maybe that's accurate enough for what they're doing. Or maybe they're doing something a little more precise and they want to the nearest like 1/16 of an inch. Right? Or maybe if you're machining a part, you want something to the nearest 10,000ths. That's still extremely accurate. But it doesn't go on forever. They don't need all those numbers. Right? So it just keeps going. So if you put all those numbers together, those are your reals. And that's basically what you study in Algebra 1. Real numbers. Each number system that we've invented was invented to answer a different kind of arithmetic question. How can you have less than nothing? How can you even have nothing? We invent the number 0. How can you have things that are parts and pieces? We invent fractions. Well, the kind of numbers we're going to look at today answer the question to a problem like that. As we've gone through, I put a question mark next to all of these. I put a question mark only because if you don't know that negatives exist, then you can't answer it. But those people that know that negatives exist, they can answer it. Right? Well, the same thing here. If I gave that to somebody in Algebra 1, they'd probably do something like the calculator is going to do. They wouldn't be able to do it. Okay? They'd say, well, it's some kind of, you can't do that. They wouldn't know why. The calculator is giving me a little more detail, but they would just write question mark. They can't do it. So, just because you don't know how to write the answer doesn't mean there isn't an answer. So if I go to on my calculator, let's get out of that. Maybe. And I go to mode, and instead of telling the calculator to work in the real number system, which is what I just showed you, I'm going to teach the calculator Algebra 2. Now, by putting it on that, it's working over here as well. So I've just taught the calculator Algebra 2 and said, hey, if you get a problem like this, we're going to invent this whole other thing for you to be able to answer that question. So if I go square root of -4 now, the calculator is not going to tell me that it's an error. It's going to tell me the answer is 2i. So we invented something to answer this question, just like we invented something to answer all these other questions. Right? So those are imaginaries. Now, if you put all of this together, these are complex numbers. Take all the reals, all the imaginaries, complex numbers. Now, if you were asking, is there anything beyond that? Is there anything like even more? I'm not really familiar with anything beyond that. And as you get to this level, the application of it isn't as simple as like, oh, negative numbers are good if you go in debt. Easy to understand. Applications of complex numbers, way hard to understand, which is why we don't get into them. There are applications in engineering. I'm not an engineer though, so even for me, when I read about the applications, it's pretty high level stuff. All we're going to learn how to do with complex numbers is basic arithmetic. Add, subtract, multiply, divide. So, complex numbers are always written in this form, a plus bi. Complex numbers are made up of two parts. They have a real part and an imaginary part, just like I showed you in this diagram. Reals and imaginaries together make up a complex number. There's an example of a complex number. 2 plus 3i. And if you write it in that order, 2 plus 3i, that is called standard form. Is it wrong to write 3i plus 2? No, it's just not standard form. Standard form is like the normal way to write it. Kind of like if you had this. If I had to write 2x, I would put 2x. It's not wrong to put x2, but we're just used to putting the number in front of the letter. Okay, it's just the way we normally do it, standard way. So, in that problem, if I asked you what's the real part, you would say 2. If I said what's the imaginary part, you would say 3. The I is just there to tell you what's in front of it is imaginary. Okay, so anytime you invent something new, it can be kind of tricky because you don't know how it's going to work with everything that came before it, right? Like if you're working on a car and you invent some kind of new feature for the engine to make it more efficient, you don't know how that feature might affect other things that were already part of the car. Right? Maybe you made something a little faster because you made the piston size a little smaller, or you made the clearance a little tighter, you get better compression, but that might affect something else that you don't know about. So, same thing with imaginary numbers. You invent imaginary numbers. We can't assume that anything we know about numbers still works exactly the same. Luckily, most of it does. Right? But we still have to be careful. So, suppose you had two complex numbers, and I wanted you to say if they are equal or not. Is this the same as this? Well, when you just have a single number, that's easy. You have one thing to compare to one thing. Like if I gave you the number 7 and said, what's it equal to? You'd say 7. Well, with complex numbers, there's two parts. You have to check a real part, and you have to check an imaginary part. So for two complex numbers to be exactly the same, check two things. Make sure that the real part and the real part match, A and C. And then make sure that B and D match. So there's an example of two complex numbers that are the same. It's not enough if only one part matches. Like let's say you did this. And I said, are those complex numbers the same? No. Part of them is the same. The real part matches the real part. Bless you. But the imaginary doesn't match the imaginary. Those are not equal. They can't be partially equal. There's no such thing. Right? They're either equal or not equal. It's a basic idea, but still something just to make sure we understand. Okay. So the last two things we're going to look at are adding and subtracting. If you understand the idea of combining like terms, that's basically how we do adding and subtracting. A is a real number. C is a real number. Those are like terms. You can combine them. B is imaginary. D is imaginary. Those are like terms. You can combine them. And that's it. So you can only combine reals with reals. You can only combine imaginaries with imaginaries. It's kind of like if you did from Algebra 1 something like this. 3x plus 2 plus 2x plus 6. You can only combine numbers with x's with numbers with x's. You can combine numbers without x's with other numbers without x's. That's basically what you're doing right here. Except instead of x, you have I. Same idea. Okay, so let's try to add these up. 3 plus 8i plus 8 plus 2i. So Max, when I combine the real parts together, what am I going to get in my final answer? How much? I think you said it.
Just for
The real parts, yeah. Yeah, just 11. Yep. So we get 11. And Anthony, what about when I add up the imaginary?
10.
10.
Imaginary.
And what do we put for that?
Squared. Oh, wait.
What if this was 8x plus 2x? What would you write?
Yeah. 10x squared.
No, if you just had 8x plus 2x, it's like if I had 8 markers plus 2 markers.
Well,
Now I have
10.
10. Yeah, I just have 10 of the markers. I don't have markers squared or anything.
So it'd be 10 imaginary.
So it'd be 10
Ah.
I, yes, plus 10i. I squared is going to come up later on, but when you're adding and subtracting, exponent on the variable never changes. Exponent on I never changes. Okay, let's look at this one. 4 minus 2i plus 3 minus 8i. Justin, what's going to be my real part here? Well, what's the real part in the first term?
4.
What's the real part in the second term?
3.
Add them up.
7.
There you go. 7. And now do the same thing with the imaginaries. Megan, what's going to be my imaginary part?
Negative 10.
Yep, negative 10i. I think we're good with that. Let's do a subtraction. So subtraction is pretty much the same as addition, except you're subtracting, not adding. The thing that some people will forget is when you're subtracting a complex number, you have to subtract both parts of it. You have to subtract the real and subtract the imaginary. So you can almost think of it as like a distributive property. It's A subtracting the C, B subtracting the D. Same rules always apply with negatives. If you minus a minus becomes a plus, things like that. It's pretty much the same thing. Okay, so let's look at these two. So example 2a says subtract the following. 4 plus 12i minus 3 plus 4i. Madison, if I subtract here, what's going to be the real part? 1. 4 minus 3. So we're going to get 1. And Isaiah, what about my imaginary part?
Maybe 12i minus
12i minus 4i, correct.
So it would be 8i.
8i, yes. That's it. That's how you subtract.
Get off this basics.
You can get that for your entire school.
Let's do it. It's free.
You can do it right now. Yeah, it's free. Why not, right? All right. Something I'm doing, so it's nice stuff. So last one, 3 minus 5i minus 8 minus 6i. Okay, anyone think they can give me the real part? Yep, Alex.
-5.
Yep, -5. Now just be careful with the imaginary part. Something's going to come up here that I mentioned. Anyone think they know the imaginary part? Yeah, Jason?
1i.
Yes, it's -5 minus -6. That's -5 plus 6. Okay, or 1i. Now, just like with a variable, you can put the 1 in front of the I, you can leave it as I. I would write it like that on a test. But if you put a 1, it's the same thing. So we've been writing I all over the place. You got I there, all these I's all over. Well, what is I? Well, I equals the square root of -1. And I put define. So if you ask me why does I equal the square root of -1? My answer would be because it is. It's like you asking me, why do parallel lines never cross? Because they don't. That's the definition of what it means to have a parallel line. Okay, there are two lines that just never cross. Why is I equal to the square root of -1? Because it is. It's a definition. As long as we all agree to use the same definition, we're fine. We just can't have different people doing different things, right? If we're all on the right side of the road, good things will happen. Don't go on the other side, just stick with this. So, one thing that we can prove is what I squared would be. As long as we all agree on that, we can figure this out. And I squared is important because it's going to come up a lot. So, we just said I is the square root of -1. That's I squared. So what is I squared? It's -1. A real number. So when you take I and square it, I was imaginary. Somehow when you square it, it turns into a real number. That's important because tomorrow when we do multiplication, we're going to get I squared a lot. If you leave I squared in the final answer, ever, you're wrong. You can't. I squared is always -1. Okay? And I'll remind you of that again tomorrow. Any questions on that? Yep.
So you can have I in the answer, just not I squared.
You can absolutely have I in the answer. This is perfectly fine for a final answer. If you wrote a final answer like this, I'd say no, there's more you can do. I squared is -1. And now simplify that to 8 minus 4 and do it up. So we never want to leave I squared in the final answer. I is okay. Okay. So homework tonight, the first part is on 308. And that's on converting the rectangular to polar. And page 560 is on adding and subtracting complex numbers. So tomorrow we will finish everything up for the week. We've got multiplication and division left. And then a couple things in 5.3 part 1. Okay, don't forget, I will be after school tomorrow if you need help. I gave everybody back their test, except I'll give you yours. Because at this point, if you haven't taken it, it's a 0. Unless you've already talked to me, then we'll take care of that. Don't forget, it's free for the entire school. It's free.